What if simply looking at something could change its very nature? I mean, what if light, the very thing that lets us see, behaves in ways that just completely defy our everyday, common sense?
It really does sound like science fiction, doesn't it? But yeah, that question is right at the heart of quantum mechanics.
Exactly. So today, we're doing a deep dive into one of the most famous and, frankly, most mind-bending experiments in physics, the double-slit experiment.
Oh, yes, the classic.
It's famous because it shows this incredibly simple, yet totally head-scratching reality that light is somehow both a particle and a wave.
Right, not just a small detail either. It's this fundamental paradox that really shattered our old classical view of reality. It kicked off the whole quantum revolution.
So our mission today is to unpack a really fascinating new experiment from MIT. It seems to refine our understanding of this quantum enigma.
And what's really cool is how it apparently settles this century-old debate between two giants of physics, Albert Einstein and Niels Bohr. A
Right.
really big deal.
Yeah, absolutely. And all this comes from a recent article published July 28th, 2025. It's by Jennifer Shu at MIT, titled Famous Double-Slit Experiment Holds Up When Stripped to Its Quantum Essentials.
Okay, so a solid source. Peer-reviewed, trustworthy.
Exactly.
Yeah.
Gives us a good foundation.
And it's just fascinating how far we've actually come in our ability to do these experiments now, to really strip them down, like the title says, to their quantum basics.
Okay, so let's rewind a bit, go back to the basics. Thomas Young, 1801, right? He did the first version.
That's the one, way back.
He shone light through two parallel slits onto a screen far away. Now, if light was just, tiny particles like little paintballs or something, you'd just expect two bright spots on the screen where they landed, maybe overlapping a bit. Simple.
Right. That's the classical particle picture. But of course, that's not what Young saw.
No. Instead, he gave this interference pattern, a whole series of alternating bright and dark stripes.
Exactly like when ripples in a pond meet up. They add together in some places, cancel out in others.
Which strongly suggested light behaves like a wave.
Right. That was the thinking for a long time. But then came quantum mechanics.
And here's where it gets really weird. The quantum twist. The stranger still part, as the article puts it.
Go on.
It's when you try to measure which slit the light actually goes through. If you try to watch its path, poof,
The interference pattern vanishes.
gone. And suddenly, the light acts like particles again, making those two simple spots. How can it be both, but only show one face, depending on whether you're looking?
And that's the absolute key. You cannot observe this wave-particle duality simultaneously. You get one or the other.
It's so fundamental. They teach in high school physics, don't they?
Oh, yeah. It's the classic illustration that quantum things, photons, electrons, everything are somehow particles and waves at the same time, until you measure them.
This deep weirdness was right at the center of that, legendary debate back in 1927 between Einstein and Bohr.
A friendly debate, apparently, but intense. A real clash of titans over the meaning of quantum reality.
You could almost picture them arguing about it.
Yeah.
Einstein, always pushing back, right? He couldn't fully accept this aspect of quantum mechanics.
No, he thought it was incomplete. He challenged the idea you couldn't see both natures. He proposed a thought experiment.
The one about the slit recoiling.
Exactly. He argued that a photon, a particle of light, passing through a slit would have to give it a tiny nudge, a slight force, like a bird rustling a leaf, was his analogy.
Okay.
And he believed you could detect that tiny nudge, that recoil, and still see the interference pattern on the screen, catch light being a particle and a wave simultaneously.
But Bohr came back at him.
He did, with the uncertainty principle. Bohr showed that the very act of measuring the slit's recoil accurately enough to know which path the photon took would inevitably introduce enough uncertainty into the slit's position that it would completely wash out the interference pattern. The wave-like behavior would be destroyed by gaining the particle-like path information.
You can't know both precisely at the same time.
That was Bohr's point. And, historically, pretty much all the experiments done since then have, in one way or another, backed up Bohr's view. Quantum theory held up.
Which brings us to this new MIT study, led by Wolfgang Ketterl and Vitaly Fedisev. It's in Physical Review Letters. They call it an idealized experiment. What makes it so idealized?
Well, they've managed to create a version of the experiment that's incredibly clean, stripped down to the absolute quantum essentials. It's almost like bringing a pure thought experiment, a Gedanken experiment, as Ketterl called it, into the lab.
How? What did they use instead of slits?
They used individual atoms, thousands of them, but acting as individual tiny slits. And crucially, they use such weak light beams that each atom scattered at most just one photon, one single quantum interaction at a time.
Wow, okay, individual atoms as slits. How do they even set that up?
Incredible precision. They took over 10,000 atoms, first supercooling them to microkelvin temperatures. That's, almost absolute zero. Basically stopped them jiggling around.
Right, need them still for this kind of quantum work.
Exactly. Then they used laser beams to arrange these atoms into a perfect, evenly spaced grid, like a crystal lattice. Each atom isolated, acting as its own perfect quantum slit.
Okay, so they had these perfect atomic slits. What was the big finding? How did they connect this back to the Bohr-Einstein debate?
The core finding was really elegant. They could prepare the atoms in different quantum states before the photon arrived. And doing this changed how much information the atom effectively recorded about the photon's path.
So they could control which path information was available.
Precisely. And they confirmed quantum theory's prediction perfectly. The more information the atom gained about the path, the more particle-like the interaction, the less visible the interference pattern became.
So it directly showed that whenever an atom gets rustled, as Einstein put it, even by a single photon, the wave interference fades.
Exactly. It explicitly demonstrated what Einstein got wrong in that specific thought experiment. The very act of the atom registering the photon's passage inevitably degrades the wave pattern.
The article mentions they could tune this by adjusting the atom's fuzziness. What does that mean? How do you make an atom fuzzy?
Right. Fuzziness here relates to the certainty of the atom's location. Remember, they held the atoms with laser light.
Yeah, the optical lattice.
Well, they could adjust how tightly that laser held each atom. A looser grip meant the atom's position was less certain, more spread out, or fuzzier, more spatially extensive, technically.
Okay, so a less precisely located atom is fuzzier. How does that affect the outcome?
A fuzzier atom, because its position is less defined, is more easily disturbed or changed by the passing photon. Its state changes more significantly, effectively recording the photon's path more clearly.
Ah, I see. So increasing the fuzziness makes the atom a better which path detector.
You got it. And by increasing that fuzziness, they directly observed an increase in the photon's particle-like behavior and a corresponding decrease in the wave-like interference. It matched the theory perfectly.
So let's connect this back to Einstein's original analogy. He talked about the slits being on springs, right? The idea was that the recoil, the shaking of the spring, would tell you which slit the photon went through.
Yes, that spring-like element, some way for the slit to physically react, was kind of implicit in many previous experiments, too.
So what did the MIT team do about these springs? Did their laser trap act like a spring?
It did, initially. The laser light holding the atoms was analogous to a spring. But here's the really clever bit. They ran the experiment again, but this time they turned off that laser trap for a tiny fraction of a second, just a millionth of a second, right when the photon interacted.
So the atoms were essentially floating freely in space, no springs attached.
Exactly. For that crucial instant, the atoms were in free space before gravity could even make them fall noticeably.
And the result? Did the interference come back when the springs were gone?
No. That's the kicker. Even without the springs, they saw the exact same trade-off. You still couldn't see both wave and particle nature simultaneously. The interference still diminished if the atom gained path information.
Wow. So it wasn't about a physical spring or recoil after all.
That's the breakthrough insight. As Fedosov, the first author, put it, the springs do not matter here. What matters is only the fuzziness of the atoms. It's deeper than simple mechanics.
It needs that more profound description using quantum correlations between the photon and the atom.
Precisely. It's about the quantum information exchange, the entanglement, not just a simple push.
This really feels like a historic clarification then. It nails down something that's been debated for almost 100 years.
It really does. And it's quite fitting, timing-wise. 2025 is the International Year of Quantum Science and Technology.
Oh, right. Celebrating 100 years since quantum mechanics was first formulated.
Exactly. And the Bohr-Einstein discussions were just 2 years later, in 1927. So this result lands right at a perfect moment to appreciate just how far we've come and how weird and wonderful quantum mechanics still is.
So let's wrap this up. What's the big takeaway for us trying to understand this?
Well, this MIT experiment, by getting down to the absolute quantum basics, has just beautifully, elegantly confirmed it again. Light and matter, too, has this strange dual nature. Particle and wave.
But you can only ever catch it acting as one or the other at any given moment. The act of measuring forces its hand, so to speak.
That's it. It's a powerful confirmation of Bohr's predictions and really shows, in this context, the subtle point Einstein missed about how quantum measurement works.
And it just highlights the incredible precision we can now achieve in the lab. Doing these thought experiments for real, it really deepens our grasp on how reality works at its most fundamental level.
Absolutely. Like, the level of control is just staggering.
Which leaves us with maybe a final provocative thought to chew on. If the simple act of observing, of gaining information, fundamentally changes the reality of something as basic as a photon, what does that imply about how we perceive everything else, larger, more complex things? How much of the world we experience is actually shaped by our interaction with it rather than being truly independent of us?
That is the deep question, isn't it? Something quantum mechanics forces us to confront, makes you think.